So, hi everyone, I'm Meera Ramesh. I'm here to present our work, Network Traffic Anomaly Detection Framework using GPUs. Uh, what is a network intrusion detection system? So, these systems, such as firewalls, capture and drop malicious traffic that intend to attack the network. So, our goal here is to develop an NIDS using the massively parallel GPUs to speed in the processing of network packets and catch the malicious network packets sooner. So let's see what is the motivation behind this. So the real-time processing of deep packet inspection is challenging. There are a large volume of packets and it requires throughput in gigabyte rate. So, so we thought we could use the massive parallel accelerator, the GPU, to accomplish this task because a deep packet inspection engine also includes signature matching. Signature matching is where we look if the payload of the packet contains malicious signature patterns. So there are lots of data and thousands of patterns for signature matching. The same algorithm is applied across them. There is no dependency between the instructions. So if there is no dependency, we can use the GPU. So, those computationally intensive tasks, such as signature matching, are moved, offloaded to the GPU to exploit the power of the graphics card and hence improve the packet processing throughput. Okay, giving a background of an IDS. So, it passively monitors the incoming and outgoing network traffic for suspicious payloads. It may be located inside the firewall before the network router. It searches the packet header and payload for malicious content. So, as we see, the NIDS is located behind the network router. So, if it feels a packet is suspicious, it calls the deep packet inspection engine. So, the engine has two parts: header checking and payload matching. In header checking, um, it looks if the packet has reserved IP addresses, if it has an incorrect checksum, or if the malicious flag bit combinations, or if the source or destination port are zero. These are the four rules that uh, we have deployed in our deep packet inspection engine. Then, after header checking, it performs signature matching. So where it checks for the packet payload to see if it contains malicious patterns. Okay. So now let's talk about the CUDA programming environment we had in our system. So we had used the Tesla K80 GPUs for our development. And what is CUDA C? CUDA C provides APIs which allow the programmer to define functions in C which are called as kernel. So kernels look like C functions, but a kernel can be launched by multiple threads. So these threads are divided into thread blocks. Threads and thread blocks can be either one dimensional or two dimensional. Also, let's talk about the memories that are available on the GPU. The different types are shared memory, which is an on chip memory. It's very fast. It takes about one or two cycles to access the data from the shared memory. And the other types of memory are global memory, constant memory, and texture memory. These are off chip, and it takes about 200 to 300 cycles to access data from these memories. So we should try to use the shared memory as much as possible. The threads in a thread block run on a same processor core and they need to share the memory resources which are limited on that core. Let's look at the architecture of a Tesla K80 GPU. So, there are 13 streaming multiprocessors, 192 streaming processors per SM. So, every SM schedules threads in a group of 32 threads called as a warp, and the total number of threads concurrently executing is 13 SMs into 16, the number of thread blocks per SM, into 1024, the number of threads per thread block. So there are 212,992 threads concurrently executing on the GPU. So what is warp divergence? Um, all the threads in a warp, a thread is made up of 32. A warp consists of 32 threads, and all the threads in a warp execute the same instruction. If there are multiple paths, the threads get diverged, and only a few threads will be active at some time. So we do not want some threads to be active and some other threads to be not active. So we want to eliminate it. So one way to eliminate warp divergence would be to have all threads in a block to follow the same execution path. So we have eliminated warp divergence in our code. So parallelism approaches. There are two parallelism approaches: thread level parallelism and block level parallelism. In thread level parallelism, each thread handles every packet. In block level parallelism, multiple threads handle a packet. So these are the two approaches we have deployed in our framework, and this is the system architecture. We obtain the network packets, and the CPU obtains the network packets using the packet feeder library. Then it all these packets are grouped into the packet buffer, and then they are sent for further analysis to the GPU. The GPU handles the signature matching algorithm, where we look if the packets have malicious data in them. Okay, what is thread level parallelism? So each thread handles every packet. So it's optimized to use fast shared memory. In order to decrease the global memory access, a Rabin-Karp algorithm is used. We were in Rabin-Karp algorithm, uh, every thread, if multi-pattern matching is applied using the Rabin-Karp algorithm, every thread has to access the global memory only m times, where m is the number of global memory accesses. So the number of the accesses that are performed to the global memory have been drastically reduced, which 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 was our goal in this. Here, as we see, each thread performs header checking and payload matching. The naive pattern matching algorithm was optimized to Rabin-Karp pattern matching algorithm. In block level parallelism, each thread block handles every packet. Thus, it's much faster than the thread level parallelism and was optimized to avoid warp divergence. How? By having threads in different warps execute the different header checking phases. Let's go and see how we implemented the CUDA based signature matching algorithms such as for Rabin-Karp, Wuman-Bohr, and the Hau-Krasik. A Rabin-Karp algorithm uses the idea of hashing. So it computes the hash value for the pattern length. So every thread computes the hash value starting from its thread index. And then it compares the pattern hash value it obtained with the signature signature's pattern hash value. If they match, then it goes and compares the entire pattern with the input. So the patterns are represented as a two-dimensional array for multi-pattern matching. And then we flatten it and copy it to the GPU. Each thread computes the hash code of every pattern, and it compares it to its hash code. It's repeated for multiple iterations. So Rabin-Karp is a single pattern matching algorithm. If it needs to be applied for multi-pattern matching, the same algorithm needs to be iterated multiple times. So it's not efficient. So we decided to use Hau-Krasik and Boomember. This is one of the fastest algorithms, There are two phases in it: the pre-processing phase and the search phase. In the pre-processing phase, the go to array, failure array, and output array are filled. These three arrays are used in the CPU version of the algorithm, but the CPU version will be optimized in the GPU version to avoid using the failure array. So the go to array is this table that stores the next state, the current state, and a character. It is represented as a two-dimensional array. The failure array holds all the states which should be reached for all those characters which do not contain a next state for this current state. So next, let's see why we do not need the failure array. So thread starts searching for multiple patterns from its thread index. So, um, so thread 0, it starts at position 0 and nothing matches. Thread 1, its start position is 1 and the pattern is he, she, his, hers. Let's let's say it it matches the patterns she and he. So in this algorithm we search using the goto array and saves the results to the output array. Let's consider the input is HERSAB. So thread 0 starts at state 0. Since it's H, it goes to state 6. Since it's E, state 7, R, state 8, and S, state 9. So at state 9, it looks at the output. Every time when it moves to a different state, it looks at the output table to see if there is a pattern that ends at that particular state. So at state 9, hers has been ended. It's ended at hers. So it comes to a conclusion that hers exists in the input text. So every thread starts from its own thread index. Like for example, every let's consider this. Let's see only the first two columns. So every thread starts working from its own thread index. So there is no need of a failure table. As I said, so thread ID 0 starts at 0, position 0. Thread ID 1, position 1. Thread ID 2 at position 2. So what is a failure table? A failure array holds all the states which should be reached for all those characters that do not contain a next state for this current state. For example, that so in the case of the GPU based algorithm, we do not need a failure table because every thread for every index there is a thread starting at it. So from every index of your input we are looking for if there is a pattern starting from that index. So we do not need a failure table that tells us to go to this position and start the search if there is no if there is no if the character does not match to those characters present at that state. So we avoided the failure table. And then the problem with the Hokorasic algorithm is that because of its large go-to table, it consumes a lot of global memory space. We were looking for an algorithm which will consume a lesser global memory space. So the Wu-Malmer algorithm is the best approach for it. So it is based on the idea of Boyer-Moore algorithm to start searching from right to the left. While searching in the text from the right to the left, if the rightmost character in the text does not match any of the characters in the pattern, we can skip searching a block of characters up to the pattern length and move the search pointer up by the pattern length. So the intuition is that this is the common case and we can skip searching many characters. So let's consider the input is Andy meet soon at Google. So Each thread starts searching from the position thread index dot x plus m minus 1. Let's consider the m is the minimum pattern length and it is 3 in this case. So it's 0 plus 3. So it's the second position. So as we see, 1, 0, 1, 2. So in position 2, that's the array index position, the thread starts searching. So threads shift based on the value of the shift table in the case of the CPU based algorithm. In the CUDA based algorithm, threads need not shift based on the value of shift table because at the distance of the shift there is another thread already working. So we shift so that we can skip a few characters and then we can start searching from that position. But in this case, we do not need to shift because at every index there is a thread that is working. So this is an optimization to Womandor which we came up that avoids the use of the shift table. Most of the threads return immediately because they don't have any characters to match against the pattern. So we look into the shift table, which determines if the suffix of the text matches that of the pattern. If the shift table says no, the shift is 0, if it doesn't match, then we just stop searching. If the shift table says the suffix match, then we call the prefix table to see if the prefixes matches. If they match, then we return saying that there is a match. So our optimizations were removing the shift table and optimizing it to launch threads in parallel. Next, let's go to the evaluation section. So here, this is the evaluation environment. We used an Ubuntu 14.04 OS, a Tesla K80 GPU with 11.25 gigabyte global memory, 64 kilobyte constant memory, 48 kilobyte shared memory per block, and 64K registers per block. The number of patterns were 100, and the packet capture mode was PCAP. So this is the evaluation between block level and thread level. Block level packet processing significantly improves performance over the thread level packet processing because we have multiple thread blocks executing in parallel for the same packet with respect to having a single thread executing for per packet. So in thread level processing, the execution time is much higher. It gradually increases with the packet size, whereas it's constant in block level packet processing. These are the execution time of the algorithm. The execution time for Ahokrasic and Womandor are significantly lesser than the Raven Cup algorithm because they are suited for multi pattern matching. It is constantly increasing for Raven Cup algorithm as the number of patterns increases because the number of iterations are more. So we conclude that we performed the packet acceleration on the GPU for packet header checking and malicious signature checking against the packet payload. And we performed performance comparison with respect to various parallelism approaches and various signature matching algorithms. And the results are that the GPU based deep packet inspection derives at least 60 times speed up over the CPU version, and the Classic and Boomamber outperform the Raven Cup algorithm. I hope I have uh, given a good introduction to the various algorithms and given specific scenarios of when you could use one over the other. Thanks very much for listening to me. Goodbye.